Come back to our beam. There is two types of beam. One is statically indeterminate. Another one is statically determinate. Both types of this beam can be solved by using the matrix displacement method. Coming back, go forward, we have for the statically determinate beam. Most of the statically determinate beam nowadays is in the form of precast reinforced concrete or precast pre-stressed concrete beam. You may see this beam in the highway bridge, okay, such as the one in the way you go to the city. Usually for the precast beam, the highway department, they just cast this beam in the factory, okay, and then during casting this beam, they build the foundation and the pier of the bridge, and they go together simultaneously, and then they lift this beam into the truck and ship it to the site, and then they use the crane to lift it and install it, and then you may see this beam going to be very convenient and easy to do. This is called a simple beam. Most of the simple beam has the pin and roller support. And there is another type of statically determinate beam, which called the cantilever beam. If you go to see the picture of your house or of your dome, okay, this is called the cantilever beam. The beam has 6 support and 3 support, and this one can be solved by using the free body diagram and the equation of equilibrium, same as the simple beam. And the last one, you also know about it since the engineering study, is called the overhanging beam. Overhanging beam. The thing that I'm saying here is, you know, if the problem is set into statically determinate, you can solve by using the matrix displacement method. But the problem going to be tougher when you compare to the statically indeterminate, because there is a lot of displacement from this problem. But I think you guys can do it. And then come to the statically indeterminate. I'm showing you is steel beam, okay, on a bridge, and also the reinforced concrete RC beam that is over here. And you can see most of the bridge that's constructed use this kind of roller. This kind of roller over here may be the pin, and most of this kind of bridge will has the support that is making the beam, to be the statically indeterminate, okay, and that is going to be our main problem in this study. So the beam in the examination can be 2 span, or sometimes can be 3 span. It's not that tough, but it requires you to work, okay, a little bit longer for the 3 span beam. And then for this one, I should mention you got to understand the step, okay. The first step of looking at this, you may just start by taking a look at the global coordinate system. And I should ask you on this, if you do this in the computer, usually you mark it, then the computer node is going to be the degree, the node number 1. And then you get the element, for example, 4 meters, and then you lift the mouse. The computer will know this is going to be the node number 2, and this is going to be the member number 1. And also you have the local coordinates like this, And if you mark this one as the 0, 0 for the computer screen, that means you setting up the global coordinate system X and Y. Okay, and then following this, you know the local coordinate system, you know the node number, you know the member number, and then you do it again. You mark this one for the node number 2 and move your mouse and your release is over here. You're going to know it for node number 3. Okay, if you move this one for 4 meter, this one will be 4, 0. This one will be 8, 0. And this is going to be member number 2. And the direction that you use is in this local coordinate. Again, if you move it a little bit further, you mark this one, and then that is node number 3 until reach over here. You get this one, the node number 4, and the computer will know this is member number 3, and this one going to be the local coordinate. And I should mention that all of the beams supposed to have this kind of local coordinate, because by doing this way, the x palm, y palm, and the xy will be the same. And then you will have lambda sub x equal to 1, lambda sub y equal to 0. This is going to facilitate your computation. Okay, your computation. And most of the time, I will provide you with this kind of local coordinate system. Don't change the direction of this, because it's going to make a lot of work to me. And then the degree of freedom of the beam can be separated actually into in the y direction and in the z direction. What I mean is the beam under the load will deform something like this. And you can see if the beam also has the settlement, so the deformation of the beam may change a little bit to something like this. And you must understand that by this way, you will have this one as the degree of freedom and the rotation, this one for the y direction, this one for the z direction. Okay, so following the global coordinate system, the degree of freedom classified into in the y-axis direction. And also the degree of freedom also can classify into the unconstrained degree of freedom and the constraint degree of freedom. And you know that the degree of freedom that follow the support, such as this one, such as this one, and such as this one, is called the constant degree of freedom. If I do a little bit modification to this problem and I provide the hanging section into this problem, okay, what we have is under the application of this portion of the beam will has the deflection also. So in this way, the y degree of freedom for this one is going to be the unconstrained degree of freedom, or in short, you may call it free degree of freedom. So by doing this, the y direction is going to be in this 4 of them. And then you must have the slope of this one. By this one, you may have this one as the unconstrained degree of freedom, because the slope can be changed when the load change, when the settlement of the structure change. Okay, and then remind you back again, the number of degree of freedom will be arranged from the unconstrained degree of freedom, such as this one. We will have this one number 1, this one number 2, this one number 3, and this one going to be number 4, and this one going to be number 5. So you will have 1, 2, 3, 4, and 5 unconstrained degree of freedom on this problem. Don't worry, Ajahn won't make that much degree of freedom. Most of the time it's going to be 2 or 3, at most 4, okay, for the B. That is hard enough. And then you have the constraint degree of freedom. Follow this one. 1, 2, 3, 4, 5. It may be 6 and 7 and 8. Let me put it in red. It may be 6, 7, and 8. So this one gonna be 6, 7, and 8. Okay, this is a guideline for you coming to this problem. Okay, this one you will have the constraint degree of freedom 1, 2, 3. Okay, that is going to be the constraint degree of freedom. That is going to be number later. And then for unconstrained degree of freedom, that you may have, let me put it in the purple. That is 1, 2, 3, 4. So this one, the unconstrained degree of freedom will be 1, 2, 3, 4. And the constrained degree of freedom will be what? Will be, let me put it in back. That is going to be 1, 2, 3, 4, and 5, 6, 7, 8. That is 5, 6, 7, 8. You can see these two problems have 1, 2, 3, 4 nodes. Okay, and this one 1, 2, 3, 4 nodes with 3 members. And then when you change the support to the structure, what happens is the degree of freedom change. For this one, if you trying to work concave, you will have this one for the constraint, and you have this one for the constraint, and then you will have this one for the unconstrained and unconstrained. And for this problem, you may have this one for the constraint, this one for the constraint. Constraint occur at the support. Again, you can do it very easy. And then you may have this one for the unconstrained and this one for the unconstrained. You see, even though simple support, you may need to invert at least 2 by 2. Okay, and for the last one that you have over here, you may have what? The constraint occur here, constraint occur here, and then you may have this one as the unconstrained, this one as unconstrained, this one as unconstrained, and this one as unconstrained. I like you to understand the first thing about the degree of freedom, because when you mark the wrong number of the degree of freedom, your calculation gonna be wrong. Okay. Next, come to our analysis procedure for this method, this pen method, and then I suppose to remind you again, since it is the displacement method, so the first step going to determine the unknown displacement. After you know the unknown displacement, you will find the reaction, and then you will find the internal shear and internal shear and internal moment. So this problem will change. From the previous one, the task, you find the axial force, but this one you find the shear and moment. And then when you combine the beam with the task, it's going to be the problem of the frame. You will find the normal force, you will find the shear force, and you will find the bending moment. Again, come to what we have discussed. You're going to sketch up the global coordinate system. Most of the time, we may mark the first one as the point of 0, 0. When you mark this one as the point of 0, 0, this is going to be X, this is going to be Y, and then when you put this one into the position and drag everything in this way, the computer will know this is going to be node number 1, and this is going to be node number 2. This is going to be the member number 1, and the local coordinate appear here. So now the local coordinate will be defined by you, by the user, and then by doing this, the x palm will follow the direction of the x, and you may see this is going to be the y palm will follow the direction of y, and again c, z, and z palm will follow the same direction. By putting the local coordinate in this way, the problem on the beam analysis is going to be simple, okay? And then you do it again by marking this one node number 2, and that is over here. This is going to be node number 3. This is going to be member number 2, and then you have this one local coordinate. Okay, now come to the degree of freedom as we have discussed, and I should tell you going first to the constraint degree of freedom. This is going to constrain because this is fixed. Okay, this is going to be constraint, and moment the slope is 0, the deflection is 0, and this is going to be constraint, and this is going to be constraint. And for the unconstrained, you can see is supposed to be this one and this one. When you put the number into it, you put this one, this 2, okay, and then you may go a little bit further. You may set this one 3, this one 4, this one 5. You got to go by the y first, and this one 6. Okay, by this number you will have the degree of freedom, the total of 6. Because you have 6, you have 3 nodes. Okay, now we come to the next one. The load that apply to the beam is not at the node of the 1, 2, and 3. The load applied to the beam is along its length. And you know, previously, the load that we used to define what we have Q1, Q2. That is going to be what? That is going to be Q sub K. It's going to occur at the node. That means you got to do something to check the uniform load, to check the point load, to apply to the node as this one. So by doing this, we just set the fixed end moment, fixed end shear, and use it to be the basis of this. Because of what? Because fixed end moment, fixed end shear will occur at the end of this member. And later, you may use the third law of what? Of Newton. The fixed end shear will apply to the node in this way. And the fixed end moment will apply to the node in this opposite direction. So come to this one. If this one is 12 kilonewton, and this one going to be 4 meter, and this one going to be 4 meter, you can determine this very easy. What? Of 12 times what? Times 8 divided by 8. This is going to be 12 kilonewton meter. So this 12 kilonewton meter will move into this 12 kilonewton meter. Okay, this see, you have this one for the node number 2. Okay, and then also for this side, you have another one that is going to be the node number 3, as you can see, and then the shear will downward over here, and the moment will be in the same same value in the opposite direction to this. Okay, this is going to be node number 3. And what we have is when you read it, you're going to what? You're going to take a look at this one. Okay, this one will follow the degree of freedom number 2. So this one is going to be your Q2. It's going to be something like this. So use your previous knowledge for the fixed end moment, and then due to the symmetry of this one, the shear, fixed end shear can be divided to be half 6 kilonewton here and 6 kilonewton here, and this is going to be the fixed end shear that apply to the node number 3. Then you're going to compare what you have. This one going to be the degree of freedom number 3, and this one going to be the degree of freedom number 2. So by this one you get the Q2 equal to this way plus 12 kilonewton meter. I will discuss this one later in step number 3. Okay, but by this way, thinking about finding the fixed end moment, okay, just follow the procedure. Usually in the previous year when we have the course book, I will ask you guys to remember the fixed end moment and fixed end shear for this one. This one going to be WL over 2 because it is what? It is in symmetry. But for the beam that has a more complex loading, someone that's like this one, I will give you guys about the fixed end moment, and you supposed to be able to determine the fixed end shear that occur over here. After you can find the fixed end moment of this beam, you may use the free body diagram and use the equation of equilibrium to determine it. Okay, and I give you the equation, okay, in the PDF file already. So let's you guys go back and practice how to determine the value of the fixed end shear and fixed end moment. I'm talking about here because there is a lot of problem about you guys on this one, and when this one when is wrong, the D sub U will be wrong. So you didn't get much score from this. Okay, most of the time only 1/3 of the total or one half of the total. So go back and review this kind of equation and practice how to determine it. And as I mentioned before, when we going to find the Q sub K, the Q sub K is the force and the moment at the node. Okay, so this one apply at the end of the members. So you guys need to reverse the direction of fixed end shear and fixed end moment, okay, and use it as the Q sub K. And also in some way, if you go back to the previous one that I just mentioned over here, you can see in the degree of freedom number 3, you have this one, the 6 kilonewton. This fixed end shear related to the Q sub U. Then when you determine the reaction, you guys must be include the fixed end shear and fixed end moment in the Q sub U. I will demonstrate this later. Okay, and then the same procedure, just taking care of the picture, list the problem carefully and check it out. Okay, what is going to be the known displacement? Okay, and then for the K. The K for the beam, the K for the beam will different from the K of the task. The K from the beam going to involve the Y and C and the Y and C, and in this direction. So this is going to be near end and this is going to be far end. And then let me talking about the K matrix, going to be something that's separate into 4 parts again. And due to this, this is going to be 4 by 4 matrix. Okay, and there is some coefficient that you must if you can remember, that is going to help you. This is going to be 12 EIL cube. Okay, and this portion is going to be 6 EI divided by L square, and this one is going to be 4 EI over L. Okay, this is going to be the coefficient of the K sub I. You must find these 3 coefficients. And why I said that? Because if you follow this one, the first portion of this one will arrange like this. And then the opposite of this also true. You just copy the value there, and then you put it into this position, and then you just put the negative into this one and this one. Okay, that's it. Going to be this portion. And then what we have is for the diagonal. Okay, you're going to put the negative here and negative here, and then you put the green value into this position, and then the light blue going to put into the same position, and then the 4 EI over L, you may just change it to half of it. This one going to be 2 EI over L. And since this matrix is symmetric matrix, you just put the purple into this position, and then copy everything that you have from the diagonal portion and put it over here. That is going to be the way you put your case matrix. Okay, follow what I'm saying. It's going to require you practices. Okay, you're going to do a lot of practices, and then after you get this, you may put this one into the same way that we have. Okay, this one cut off, this one cut off. Why? Because the beam has no axial force, and then has no axial deformation. So you just cut this portion, and when you cut this one, you got to cut the first column and the fourth column. You take care all the end out. Okay, on the end is going to be the axial force out. Okay, and then you set up this way. The lambda sub y is 1, lambda sub x is 1, lambda sub y is 0. So this term just gone. This just be 1. Okay, this just be 1. This just be 1. What I'm saying is this is going to be the green. Okay, that I tell you before, and this one going to be the blue. Let me put the green. Okay, this one going to be the green. Okay, and this one going to be the green with the negative over here, and this one also the green with the negative. See, and then I said we have the blue. Okay, the blue and this one portion is the same. Because of what? Because it's symmetric matrix, and then this one going to be the yellow. Okay, and then you just copy this yellow over here. You just copy the light blue over here and putting the negative side in front of it. That is not that tough. It's just from the derivation that we talking about before. Just put it over here and put it over here. There are total of 6 negative sides. And then what we have, you do again for the copy. Okay, you copy the light blue over here. You copy the light blue over here. Okay, and the last one, I do that the purple. just put the probe hole here, and the probe hole gonna be come here. Then you may just make a copy, and not a copy is symmetry. This one and this one going to be symmetry, and then you put it over here. So this is the way that I need to tell you, and let you guys to decide the way you taking care of the K matrix. Okay, don't thinking about I will go back and take a look at it during examination. No, by this way you going to take a lot of time to work on it, and then you said, Ajahn, the problem require a lot of time to work on it. No, I ask you guys to practice on this in order you guys to have a good skill, okay, and you can apply that skill to put the coefficient into a proper position of this very simple. This is simple. If you work for the frame, it's going to be harder. That's why we start from the task and then come to the beam and then later to the frame. Okay, and you're going to use your skill that you are going to use it in this coming Sunday on the examination of the class to assemble the small K matrix into the capital K matrix. It's going to require the same skill, and then the compute for the unknown displacement, you using the same skill. Compute for the unknown force, you're going to use half of your own skill, because after you get Q sub U for the task, you use it. The reaction, you use it immediately. But for this one, you cannot. You need to combine your Q sub U with your not actually it's not fixed and shear moment. It's going to be the reverse, okay, reverse, SE reverse, fixed end moment, fixed end shear at node, okay, that's I'm showing you for the number 3, okay, and then you may find the small q. Following this one, the small q usually determined from this equation, but by setting the lambda sub x equal to 1, lambda sub y equal to 0. This matrix is going to be the identity matrix. When is the identity matrix, it's going to be the same thing as the number 1. Okay, it's going to be the same as number 1. And then you can use the K. This K from the previous one, from the what, from the this step, yeah, you can use this one, and then you just time it by the D. Okay, I may recall you a little bit about the member of the beam. Okay, it has this way of local coordinate and degree of freedom N, Y, and then N, Z. This is the near end. For the far end, it's going to be F, Y, and then F, Z. Okay, and then what we have is going to be the D over here will be D sub N, N, Y, D sub N, Z, D sub F, Y, and D sub F, Z. That is going to require here. But after you compute this one, it's not finished yet. Okay, you got to put your Q with your fixed end moment and fixed end shear to get what? To get the free body diagram that's used to draw the shear diagram and moment diagram. So don't forget about this. This step didn't have for the task to do it, okay? But for this beam and frame, you got to do so. That's what I'm saying. When I cut the problem in this way, one of the problem maybe the frame or the beam, I cannot tell you, but you guys are supposed to go back and work on it, okay? And now come to the example. Let us consider this beam. This beam has the stiffness of EI, both member number 1 and member number 2. You set up the global coordinate system, and then you see we have the node here 1, 2, 3, member number 1, member number 2, and the local coordinate direction. I tell you already, we will set up in this way in order to make our problem easier. And then what we have is the degree of freedom. What degree of freedom is the constraint degree of freedom? This one constraint, this one constraint, because this is the fixed support, this one constraint, and this one constraint, because it's again is the fixed support, and this one is the constraint, because this one is the roller. So this problem is going to be very easy. You have only this one as the unconstrained degree of freedom. Have only one. Okay, let me start by this simple one, and the next problem I will show you. Usually I didn't make the examination have only one degree of freedom like this, but this simple example will help you understand the problem easily. Okay, then the second one, you got to use your previous knowledge to determine the fixed end moment and fixed end shear that occur on this beam. Okay, this fixed end moment at node number 1, at member number 1 on the left. This is fixed end moment at member number 1 on the right. Okay, and then you guys know about this. This is this is uniformly distributed load. WL square over 12, you can find a fixed end moment easily. So this fixed end moment gonna be 75 and 75. And then for the fixed end shear, you just put the shear at the end of this one, and half of the load will provide to the left, and half of the load will provide to the right. So this is only 3 meters. So this is going to be 75 kilonewton, and direction down upward. Okay, now we got to use the limits of this fixed end moment, fixed end shear to apply at the node. This is the node number 2. The node number 2 has what? Has the degree of freedom number 1 and number 2. And then you just transfer the 75 kilonewton meter for the moment. Okay, so your Q sub K gonna be very easy. Just see the direction of the pink and the red, the same direction, so it's positive. And I should tell you that this is going to be Q sub 1. And how about what you have for the Q sub 2, Q sub 3, Q sub 4, Q sub 5, and Q sub 6? That is going to be the unconstrained degree of freedom. This all Q gonna be what? Gonna be the reaction force and reaction moment. Okay, by doing this, let me put 75 over here. Okay, this is going to be 75 kilonewton shear, upward, change to downward, upward, change to downward, 75 kilonewton. And then the fixed end moment is also applied over here, 75 kilonewton meter. See, by doing this, I should read this one. This is 75. Direction of number 2 here is the opposite. So you must minus it with 75 kilonewton. That's for what? To determine the reactions. Okay, after you determine the D sub U, you will find the Q sub U. And then go to number 3. That is going to be minus 75 kilonewton. And for number 4, okay, the green and the blue in the opposite direction, minus 75 kilonewton meter. And then for this one, there is no applied loading. So this is 0 and this is 0. This is going to be the matrix that you use to determine the reaction later. Okay, I must mention it here to make you clearer. The beam has no deflection. Okay, the beam has no deflection. So the deflection is going to be something like this. Okay, and then the member, again, I'm going to tell you this green one, you must put it into 12 EI over L cube. You get this one. For the blue, if you remember my coding, you just put this one and you can see the coefficient is in the form of the function of EI. And then the last one, you have this one. For the other one, for 2 EI over L, you just divide this just by half. And again, this is going to based on this is near end, this is far end. When we talking about this, the coordinate, the degree of freedom that's associated with the K1 gonna be 3, 4, and 2, 1. Okay, 3, 4, 2, 1. That is going to be the degree of freedom of this. And then you just put everything that I tell you guys about this. And if you prefer to do so, okay, and actually you have that in your hand already, just make the symbol into position. This is green, this is light blue, this is yellow. Just put it like this, and this is going to be the light blue. Just put the light blue over here and light blue over here. The green, put it over here, and the yellow, put this yellow over here. And don't forget, just don't forget about the negative, negative, and negative, 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 6 of them. And then again, you guys just try to put this one, and then the light blue going to be this one and this one, and then you divide 4 EI over L over here by half. Let me put this one in the light yellow, okay, and then you copy this 2 EI over L over here, and then you just put your green over here and light blue into the position. And then what you have is the matrix that is going to be symmetric matrix, okay, and then you guys supposed to check it to be in the like this one and this one the same, this one and this one the same, this one and this one the same. See, yellow and this one and this one and this one. So that's called the symmetric matrix. So you get this. After you get the number, you just follow what I show you. And don't forget, for this kind of problem, there is the EI in front of it. Okay, because this is a function of dot modulus of elasticity, times the moment of inertia. Okay, and then when you do this, you go to the second one. You do the same. For the second one, you have this one as the near end, this one as the far end. What is going to be the order of the degree of freedom? It's going to be 2. 2 going to be 2, 1, 5, 6. Okay, and again, you have this one to be the green. You have this one to be the light blue, you have this one to be the dark yellow, and then you do the same thing that I just mentioned. But don't forget about the order of the coordinate 2, 1, 5, 6. Okay, and you may see the order of the degree of freedom for the beam's member. The order type of strength when compared to the thrust. The thrust sometimes you can rearrange it to be like 1, 2, 3, 4, or maybe 1, 2, 7, 8. That's going to come come like that. But this one, see, it's going to be 2, 1, 5, 6, something like that. Okay, and then you do the same thing. That is going to be the same number. I use green, replace this 4, and then this I use the light blue, okay, to replace this, and then I use the dark yellow, replace this first one, divide by half. So the S symbol of the K1, small K1 matrix and small K2 matrix gonna use some skill. Okay, let me do it to show you. We're going to start by this one. This is what this is going to be degree of freedom number 3. We start with 3. You may just put 0.05 and 6, something like this, and then you must be very careful. Next, what is going to be that is going to be okay, this is going to be 5, and it's going to be this one going to be number 4. It's going to be 0.1667, and then it's jumped to number 2, and then it's jumped to minus 0.05556, and then you jump to number 1, 0.16667, as you may have. This one going to be 1, 2, 3, and 4. Don't forget the EI. And then go to the low 4. Low 4 is over here. Again, you start with 3. 0.1667. Do it carefully. Number 4. 0.6667. And then go to number 2. This one minus 0.1667, and then go to number 1, 0.3333 and 3. See the significant number that I use. You also significant, okay, significant number here that's going to use. You must use at least 5 of the significant number during calculation. If not, your answer may be wrong. Then we come to number 2. Okay, number 2 start with 3. This one minus 0.05556, and then go to number 4 minus 0.1667, and then you jump to number 2, 0.05556, and then you jump to number 1 minus 0.16667. So what we have is this one first, 3, 4, and then 2, and then 1, and then 3, and then 4, and then 2, and then 1. And the last one I like to show you guys about it is going to be 1. Just start over here. That is 0.1667, and then go to 4, 0.3333 and 3, and then 2 minus 0.16667. The last one 0.16667, and then you may get start by here, by here, by here, and by here. And if you are very prudent, you may check over here. Is it going to be the same? It must be the same. This one in the opposite. No, in the symmetric matrix. Okay, and then you may check a little bit about this one. It's going to be this one going to be this one, and later you may check this one by this one. This is going to confirm what you do for the S symbol of the matrix. Okay, to make you more understanding, let me move a little bit to this one. This is 2, 2, 2. Okay, this is going to be 2. You start it by 2 over here, so it's going to pass 0.02344, and then go to the number 1 plus 0.09 3, 7, 5, and then go to number 5. You come to over here minus 0.02344, and the last one 0.09375. So you get what you have. This one, okay, correct. This one, correct, and this one, correct, and this one, correct. Do it slowly like this, and 1 over here start with 2. So you come to row number 1. You start with this number 2. So plus 0.09375, and then plus 0.5, and then minus 0.09375, and the last one is going to be 0.25. Just put it like this. So the first one, the second one, the third, this one, 5, third, and the fourth. Okay, and then you do the same like this for the author, and you can see they didn't require much computation. Okay, only few copy. Is going to need the summation. But as for this one, you need to have summation. If you're very good in the mathematics, you don't need to put it into the calculator. You know what it is. Okay, this one, the second one, and then if you know this one, you may make a copy into this one, and then you have the third one to do it. See, the author, you just make a copy into this, and then if you check the symmetry, you will see that the matrix, the capital K matrix, also the symmetric matrix. When you finish it, don't go further, check it first. This is going to be the symmetric matrix, such as this one. And if you go for this one, check this one, check this one. You may use your highlighter to check it, as I did show you before. And then for the author, just change the color a little bit, so you can take a look at it, okay, easily. You won't mess it up. This one, you may have this one, and this one, you have this one. Check them. You need to make it to be correct before you go further. If not, you will have the incorrect answer. Now, you have only Q sub K. Your Q sub K only have the Q1. So this is the Q1. And then the unknown displacement, only to have only one member. This problem is going to be very easy for computation. The last part of this, making it to be 0. You just reverse this number. Don't forget about EI. EI also needs to reverse. Okay? And then you get this one as the answer. And then this is positive. It's gonna follow this direction. So based upon this, the rotation, the slope that occur here must be in the same direction as the D1. And then if you are using your own knowledge about drawing the elastic curve, you can see this one supposed to be go downward due to this force, and then this portion must be reversed to have the tangential line over here, and then over here it must reverse back, something like this, in order to go to this fixed support. That is going to be the shape of the elastic curve due to this counterclockwise direction, and then you get very similar elastic curve. Okay, and then Q sub U. Okay, this one can be computed. This one 0, and then just cut this one out. Only this portion will time with the deflection, and then E cut E, you get this. This is the Q. It's not the reaction yet. Okay, you got to put this portion into the calculation as we did before. So you need to find the complete Q sub. Let's see, this is going to be Q sub U matrix. Q sub U matrix will require this white block to put into kit. I did show you guys already on this. Okay, and then this is number 2. This is minus 75 kilonewton. This is number 3. This is minus 75 kilonewton. This is number 4, right? This one, the degree of freedom, number 4. This is opposite direction. So this one going to be minus 75 kilonewton meter. You get it. You plug this one back over here, and then you can do the computation by putting them together. So this is going to be the reaction, moment, and shear. No, is the reaction, force, moment, and force. And then you must check the equilibrium of this. Okay, you may check the combination of this one. You have this one for 25 times 6. Okay, this is downward. This is upward. This is upward. This is downward. You may check the combination of these 4 values, whether it's going to be 0. It must be 0. Okay, to make it correctly. If not, just go back and time to work on it. Okay, that is going to be the correct. And then if you're very sure that is correct most of the time, if they are in equilibrium, your computation gonna be correct. It means your D sub U is correct. And then come to the small q. As I show you over here, since the lambda sub x equal to 1 and lambda sub y equal to 0, this is identity matrix. So you may use the K from the previous step, okay, to taking care of this. And before you compute, just check your degree of freedom orders. That is going to be 3, 4, 2, 1. And then the D, this is going to be D3. This is going to be D4. This is going to be D2. And this is going to be D1. And for this, you don't need to do the putting everything into the calculator, because this first one all are 0. Only for this one time, this one, you will get the first number here. Okay, and then for the second one also, you may time this one by 0, this one by 0, this one by this 0, and then the second one going to be this one, and then the same thing. This one will time 0, this one times 0, this one times 0. So only this one times this one, you get this one. Okay, for the previous one, you will get this one. And the last one, let's duplicate. This is times 0, times 0, times 0. Only this one times this one, and then you get this one. Is this going to be the shear force? Going to be the end moment? Not yet. Okay, we will talking about this later. Just keep it over here. For the second one, the order gonna be 2, 1, 5, 6. Okay, that is going to be D2. Okay, and then this is going to be D1, D5, and D6. You do the same thing. There is a lot of 0 here. So this one times 0. So only this one going to time this one has the value for the first one. Gonna be from this one. And then if you do it again, repeat it. This one gonna have this one to make this one. And only the second column going to time this one and get this value, and I should tell you again this one time this one, and then you get this value. Sometimes you don't need to put a lot of things into the calculator if you work on the problem more enough, you get a proper skill and you can do so. So what you have from this computation must combine with the fixed and shear, fixed and moment, because this fixed and shear, fixed and moment at the end of the member, we didn't use it yet. Okay, we just use the fixed and moment, fixed and shear, that's levers, and use the third law of Newton, move into the node. And then by doing this, you got to make it correctly. I should mention about this axis again. Okay, this axis will set the local coordinates x prime, y prime like this. That is going to follow the global coordinate x, y. The same thing of this. This is x prime. This is y prime. Then I said, if you use the other direction, the problem of the beam going to be harder. You may try it later, but for my examination, just follow this. It's going to help you. Okay, the force here Q3 is upward, and Q2 in the member number 1 going to be downward. Okay, and then you put the moment. The moment Q4 21 is going to be like in this direction, follow the right arrow, and this one also put it over here. And then for the second member 6.027 and minus, this is going to be the minus. And then the moment 32.143 and 16.072. This occur at the end of the member also. So you combine them together. Okay, the first one, you have what? This one and this one, you have 85.716. And then you combine this one in this direction with this 21.428. You got it to 96.428. Now 72 upward, and this one is downward. Gonna deduct 75, and then you have up, and this is not correct. Okay, this is 75 and 42. It's going to be something. No, it's not going to be this. It's going to be. I'm not sure. This is wrong. Sorry, I'm making something wrong. It's not this one. 75 must be interact with this one. Is in the opposite direction, so it's going to be this one. And for the moment, the other thing that is for the moment 42.875. This is moment, and this 75 they must combine to be in the opposite direction. Not combine in the opposite direction. It can be 32.143. So be careful about this. For the next one, just make a copy complete, because this fixed and shear fixement is 0. Just make a copy complete. So that is going to be your work, and then you got to use your free body diagram, draw your shear diagram, draw your moment diagram, and then by doing this, you know, this is going to be what? Going to be the inflection point. Before that, we didn't check the inflection point for this. We have 3 inflection points for the steel beam. Inflection point, not that kind of very important, but for the reinforced concrete, is going to be very important. Don't forget about the point of zero shear that's produce the M positive M max over here. This is going to be negative M max over here. Okay, most of the time we require you guys to determine the V max and moment max. Okay, due to the matrix calculation, we must use at least 5 significant figure. Okay, so let me finish this portion of lecture here and move you guys to the problem that we have last year. Okay, just for your reference, so you guys can see what you did in the previous year and what is going to be in this coming year. I will take some time on this problem because I like to make it very detailed in order you guys can have experiences with this one. First, read the problem carefully. This one has the modulus of elasticity of 200 times 10 power 9 Newton per square meter. But the problem that we are working on, the unit of force is in kilonewton. So you are supposed to change this one to 10 power 6 kilonewton per square meter. And then the moment of inertia is 1.36 10 minus 3 meter power 4 already. So it's going to be EI. EI is very important. 10 power 6 times 1.35 and 10 minus 3. Then you must cut this one and this one change to 3 and time this one you will get this one for 270 10 positive 3 and then that is going to be kilonewton time meter power 4 divided by meter square. That is going to be the unit of this. And then as I tell you, it's very important to determine the coefficient of each member. Let's say this is going to be the member number 1. Okay, member number 1 is 6 meter for the member number 2. Number 2 is going to be only 3 meter. So you just do it and it will use it later in the computation. This is going to be 12 times 270 times 10 watt power 3 and divided by L cube. Okay, L cube is 6 power 3 by divided by 6 power 3. You get this one for 15,000. And then for the next one, 6 EI over L square. So it's going to be 6 times 270 10 power 3 divided by 6 square. Now you get this one for 45,000. Okay, and the last one, let me put it in back. This is going to be 4 and then EI and then divided by L. So the number, the last one going to be larger than the previous one. You get this one for 180. This is the stiffness that we have for the member number 1. Now we move to member number 2, 12, and then EI, the L just change. Okay, and then do it carefully. It's going to divide by 3 cube, and the number going to be very large, 120,000. For the second one, again, you use the same one, 6 times 270. The problem is easy. We can change one of the member to be another EI. Okay, and then you must do it. If you make things wrong over here, you're going to correct only Q sub K and D sub K. And then this is 3 square, 180,000. And then the last one, the 270 EI 10 power 3 and divide only by 3. That is going to be 360 3,000. Okay, this is going to use for the K. Then they ask us to find this one. This one is going to be D sub U. And then you're going to find this one. This is going to be the Q sub U. Okay, this is going to be Q sub U. This is going to be D sub U. Very last score for this. And then you draw the shear diagram and moment diagram and draw the elastic curve. Okay, last year we have this problem for 2 hours. So I provide you guys with a lot of time on this. But for this one, we didn't have much on this. So I will select one of the problem for this. And then we come to determine the D sub K. Before you go further, based upon this problem, you got to set the global coordinate system. Even though it didn't help you over here, please do it to be a complete of this problem. Okay, and node number, local number, the member number, we already have it. So it's going to be very convenient to do so. And the problem also said there is the segment occur here for minus 0.010. That is going to be about 10 millimeters. So this point just move downward over here. When this point moves downward, the deformation of the structure may become in this way. Okay, sometimes it's going to recall back and going to be over here, zero slope and zero deflection. So they're supposed to have the inflection point somewhere here, and over here also be curved. Okay, and what next? We can find the D sub K easily. And let me move the D sub K over here because I require to work on it. For the D sub K here, we have what? The degree of freedom must be classified into the constraint and unconstrained. Okay, and you can see the degree of freedom constraint is at the support is lower, so constraint over here is lower, constraint over here is fixed, constraint. So we will have only two unconstrained degree of freedom, D1 and D2. So the known displacement that we known as the support, that is going to be D3, D4, D5 and D6, and then following this 4, 5, 6 is 0, but at the 3 this is going to be the downward and is downward for 0.010 meter. So this one will be minus 0.010 meter, and then D4 this is 0 meter, D5 0 meter. This is slope. This is slope. Okay, so this is 0 radian. So you have this one will be need to classify segment between the direct or the linear displacement with the rotation displacement. Sorry, I didn't show you on this. Anyway, by doing this, okay, it's going to be easy. And then the beam that we are looking for, the beam number 1 is going to subjected to a complicated load because it has both uniformly distributed load and the uniform load. Let me working over here in order us to have space to work on it. Let me scale the portion. This portion 6 meter for 3 centimeter, and this one only 1.5 centimeter for 3 meter. And what we have is this portion going to be simple because it's subjected to only the 6 kilonewton per meter, but this one has the uniformly distributed load of 12 kilonewton per meter, and also this one for 20 kilonewton. This is I didn't put it much. This here is a special here. I just put this moment into at the middle of this beam. What happened is for this one is going to be very simple. We're going to have this shear force. This shear force is going to be WL over 2. This is going to be 6 times 3 meter divided by 2. This is going to be 9 kilonewton. Okay, and then what we have also the fixed end. We have WL square over 12. We also have this one. This is going to be what? 6 times 3 square over 12. And then this one divided, and then this one 9 divided 2. This is going to be 4.5 kilonewton meter. So many times you don't need to put everything into your calculator. Okay, just use your skill to do the computation. But for this one, the load separate into 2 portions. The first one is due to the, let me put it into the moment, okay, over top of this. And the second one is maybe due to the uniformly distributed load. Let me work on the uniformly distributed load first. So it's going to be easier, and then we'll be combine them later. Again, this one we have the shear, fixed end shear, and then our fixed end shear gonna be what? 12. This is 12 kilonewton per meter, and time what? L is going to be 6, and then you divide it by 2. Okay. What you get is going to be half of this 12, and then time, actually half of this is 3. Okay, and that is going to be divided. It's going to be 6 times 6. It's going to be 36 kilonewton for this. And next, again, what you have is the WL square over 2, 12 times 6 square over 12. So cut. This is going to be 36 kilonewton meter. 36 kilonewton meter. Okay. We will have another one. This is going to subjected to this 20 kilonewton meter. Yeah, you got to go to what we have on this one. Let me show you. I did provide the student with this kind of fixed end shear, fixed end moment, and by doing this, the A and B is equal. So this one will change into the M over 4, and this one will change to 3M over 2L or 1.5 M over L. Okay, and basis upon this, see, this is the direction, and this is going to be the end shear. This one downward, this one upward, and then if you put it into this, you may compute it to be 1.5 times 20, and then divided by 6. Okay, that's one going to be 30 divided by 6. That is going to be 5 kilonewton, and this is going to be 5 kilonewton. And then you can compute for the moment. Let me put it into the blue. The moment gonna follow the direction over here. Okay, this one gonna be up, and this one gonna be down. And then you have this one to be 20 M over 4. That is 20. That is going to be 5 kilonewton meter, right? If I'm correct, it's going to be 5 kilonewton meter. and then you need to combine them together. Let me move this one to here. What we have is the blue and the black. Okay, when you combine them, this is going to be 41 kilonewton, and then the shear here, that is 5, that is 36. Also we have this one for 41 kilonewton meter. Okay, this one 41 kilonewton meter, and then this one and this one is going to be in the opposite. This is 5 kilonewton meter, this is 36, and then the 36 must be what the is larger. It's going to be 31 kilonewton meter. This one 31 kilonewton meter, and the shear also in the opposite 5, and the shear here is 36. So it's going to be upward with the 31 kilonewton. So if you coding it, it's going to be easier to compute. Let me check this one out, and I will move this Q sub K into this. And following what we have here, we have only Q1 and Q2 for Q sub K. By doing this, you got to draw the node. Okay, we have the node here. This is node number 2. This is node number 1, and this is going to be node number 3. And then you just make the reverse of the fixed end shear, fixed end moment by using the third law of Newton. This is going to be 41 kilonewton meter, and this is not correct. This one and this one kilonewton meter, and I did this wrong. Okay, 5 and 36, that is going to be the 41 kilonewton. So this one will have to 41 kilonewton. Okay, and now this one going to be a little bit more compact. This one going to be 31 kilonewton, and this one going to be 9 kilonewton, and this one going to be 31 kilonewton meter, and this one going to be 4.5 kilonewton meter. This one require a lot of computation. Let me move this one to the next one, and you can see when you combine this one and this one, you get it for 40, right? You get this one for 40 kilonewton. 31 and this one is 4.5 or what? Let me check. Okay, this one is 4.5, and then you combine them and you get this one is the 31 minus 4.5 is going to be 26.5 kilonewton meter. Okay, and then the last one over here, you get this one 9 going to be downward. Okay, 9 kilonewton, and then the moment here is going to be 4.5 kilonewton per meter, and then we come to our degree of freedom. This is going to be the degree of freedom number 4, and this is going to be the degree of freedom number 1. Let's put them together. This is number 3, and you may put this one in this way. This is going to be number 3, and this is going to be number 2, and then this is going to be 5, and this is going to be 6. What you require is the degree of freedom number 1 over here, and degree of freedom number 2 over here, and you can see 41 related to the degree of freedom number 1 will provide the negative because they are in the opposite direction. So this one minus 41 kilonewton meter, and the other one is going to be in the same direction, plus 26.5 kilonewton meter. Okay, and we use only 2 of this. We still have this one for number 4, this one for number 3, and this one for number 5, and this one for number 6. That's one going to related to the constraint degree of freedom, and it will be used in determining of the reaction. Let me put them together. Okay, let me put them together. We have Q3, Q4, Q5, and Q6, and then they are related for the Q3. You can see the 40 is downward, so minus 40 kilonewton. For the Q4, 41 get downward, so minus 41 kilonewton. How about for the Q5 over here? This is downward, that is minus 9 kilonewton. And 4.5 and D capital D6 go together, has 4.5 kilonewton meter. And then this is going to be the matrix that we are going to use it to determine the reaction. Okay. And next, come to determine the small case matrix, and then we use the member number 1 first. On the member number 1, we have the degree of freedom as shown over here. It's going to be 4, and then 1, and then 3, and then 2. And then that's mean by doing this direction for the near end and far end, the degree of freedom, the order of the degree of freedom, YC is going to be 4, 1, 3, 2. Okay, that is going to be 4, 1, 3, 2. And now we come to the number that we had before, and if you may remember, we may divide this one into 4 blocks, and the first one we may put it is going to be this one, and this one going to be 15,000, and the second one, this is going to be 45,000. You just rearrange it into the order, and the third one, that is going to be 180,000, and due to the symmetry of this matrix, this is going to be 45,000. And if you remember, you got to put the negative, and negative here due to the symmetry again. And then this is going to be 15,000, 45,000, 45,000, and 180,000. And then you copy everything again except this one. You got to reduce it by a half. It's going to be 90,000, and this one also going to be 90,000. And then things going to be very easy to follow. Okay, just do it. It's going to balance your brain also. And then this going to be compute this 15,000 45,000. It's just require practices. Okay, you guys can do so. You are an engineer, you can do it. Engineer can do everything, reduce the work, and then come to the second member. Okay, and on the second member, again, I will draw the member over here. This is going to be a shorter member. This is going to be near end. This is going to be far end. This is going to be the direction of this, and then the degree of freedom that you got follow 3, 2. This is going to be 3 and 2, and then 5 and 6 and 3, 2, and then 5, 6, 3, 2, 5, 6, and divide this one into 2 portion, 4 portion, and again you're going to go back and take a look at your number. What you have for the number is going to be over here. Okay, let me put it in the first block. The first block is here. This is 120,000, and then this is going to be 180,000, and this one going to be 360,000, and by the symmetry, this is 180,000. And then if you have this, you may move this one out. Okay, and don't forget what we have before: minus, and then minus. Make a copy of everything. 120,000, 180,000, 180,000. You can see the small k matrix also the symmetric matrix. Okay, and this time we don't have EI. some people confused. Some people taking a look at the example and then put the EI over here. No, we don't have. We combine the EI into our computation from the first step. So it's different from the previous one. Okay, this one we know the EI. The previous one we don't know the EI. You may put this one for the K1 and this one for the K2 if you prefer. And then 120,000, 180,000, 180,000, and then this half 180,000. Okay, and then minus 120,000, 180,000. Make a copy, and then to make it to be symmetric matrix. Okay, and then 180,000. That is going to be our matrix, and then you're going to combine them into this matrix. This capital K matrix is going to have the total of 6 by 6 member. So this is going to be 1, 2, 3, 4, 5, and 6. And then you got to do it as previously I did show you. I'm going to show you again because this is important. It's kind of a review for your task also. Okay, this is what 4. You start by 4, and then 4 is here, 115,000, and then from 4 you go to 1. Okay, 4, and then you jump into 1. That is going to be 45,000, and then you jump into 3 minus 15,000, and then you jump into 2. Just remember the way you work on it. Okay, and next go to number 1, and then number 1 with what? Number 1 with 4. Okay, you start here, 45,000. So jump into 1. That is 180,000. Jump into 3 minus 45,000, and then jump into 2 over here. That is 90,000, and then you come to number 3. Number 3 with 4. Number 3 with 4 is here. 15,000 and 45,000 go to 1, 45,000, and then go to number 3, that is 15,000, and then number 2 is here, minus 45,000, and then we come to number 2 and 4, 45,000, jump to number 1 over here, 90,000, and then number 3 minus 45,000, and then the last one minus, okay, that's not minus, yeah, this one 180,000, and I like you guys to check whether it's okay or not. For this one you got to check the symmetry. Even though you move it already, the member of this always to be the symmetric matrix. See, and that means you are in peace of mind if you can do this. Okay, and then a little bit further, go to this one, number 3, and then start with 3 plus 120,000, and then go to 2 over here, 1 plus 180,000, and then go to number 5. Number 5 is here. Okay, that is 120,000, and then go to 6, 180,000, and you move to number 2. Number 2 start with 3. Number 2 start with 3 plus 180,000, and then go to number 2. This one plus 360,000. You can see if you use the different color, it's going to help. Go to this one, 180,000, and then the last one, positive 180,000, and then go to the number 5. Number 5 start with 3, 120,000, and then go to number 2 here, minus this one, minus 180,000, go to number 5, 120,000, go to number 6, minus 180,000, then number 6 start with 3, 180,000, and then start with 2, 180,000, and then minus 180,000, that's 5, and then 6, 360,000. And then if you prefer, you do the same thing, check the symmetry of this symmetry. Okay, this is going to be in symmetry. If it's symmetry, your life is going to be happy. And then okay, the last one is here. Then if this one is symmetry, I think everything must be easy to follow next. Okay, next we put everything together to draw the big picture of this task. Let's see, one is not enough. Let me put this one. Okay, and then let me start by 12. 6 times 2 is 12 what 12 centimeter, and then you may put this one to the reference, 1 2 3 4 5, and then 6, and then you mark it. Okay, and okay, that's require a lot of work. I take to lecture, it's going to be very tight. Okay, 1 2, and then 3 is over here. Okay, and then 4. Okay, and then 5. That is 1 2 3 4 5, and the last one gonna be 6. Okay, let me put the 6 over here. Okay, and then this one will up something like this, and this one will finish here. You have 1, 2, 3, 4, 5. And then put 1, 2, 3, 4, 5, 6. And then over here, you just put the matrix Q. Okay. And over here, you must put the matrix capital D. And what we have is going to be only 2, right? So this one will separate by the partition basis upon the first only Q1, Q2. So it's going to be divided into partition like this. And then you copy what you have to make a combination, okay? And basis upon this, for the Q1, you have it before. For the Q1 and Q2, oops, that is a little bit too much. Q1 and Q2, see on the top of it. Okay, you have, okay, this is minus 41. Why I put this? Because the Q, okay? And then positive 26.5. And then I have this one, Q3, Q4, Q5, Q6 is going to get along together, and then just put this one into okay, and then Q3 minus 40, minus 41, minus 9, and then plus 4.5. Okay, just erase this one a little bit to make it clearer. And this one going to be D1, D2, and then you have the deflection here only minus 0.0010, minus 0.010 meter, and then 0, 0, and 0. But basis on this, okay, you got this one. And then a lot of things you can put them together. See, it's not that hard. It's require you to input only some of them. The computation is not that tough. This is going to be 180,000, and this is, I will work like this because I know it's going to be symmetric matrix. So I'm going to just put the first portion of this, and then I will copy everything later. Okay, this one gonna be 45,000, 0, 0, and this combination gonna be 540,000, and this is going to be minus, and minus 45, 135,000. That is 45,000, 180,000 plus 180,000. You may put sign into it if you prefer to make it a little bit clearer. And this one is the same thing, okay? And this one is going to be 135,000, and this one minus 15,000, and minus 120,000 plus 180,000. Okay, and then this one 15,000, 0, 0, 120,000 minus 180,000, 360,000. Okay, and then you make a copy everything like this. This is 90,000 minus 45, this one minus 45, this one positive 45,000, and then 0 and 0. See, and then if you prefer, just put 180,000 and 0, 0. No, sorry, this one positive 180,000, and this one 0, this one minus 180,000. See, it's not that hard. This plus 135. So by putting this, your matrix will be in symmetry, and then we will check the correctness of this later when we determine the reaction. Okay, and this is minus 180,000. Okay, this is 15,000, and then 120,000. This is positive, right? And then this one, just put it here. So you get this one, and this one supposed to be in a very order. And now you are ready to compute for your solution. Now you will have to set up something to make it in a good format of computation. Let me zoom in a little bit on this. You may have the this one is Q sub K, and then this is going to be your K11, and time this one D sub U, plus this one is K12, and then time this one to be D sub K. And basis on this, I said I'm going to move this one. So your Q sub K minus K11, and then D sub K. And this one you will know is going to be the column matrix and equal to K11, and then time K11 time D. Let me put this one a little bit. Time D sub U. Okay, and basis upon this, you can reverse this one. I may put this one D sub U. Okay, is going to be the inverse of K11. You got to show your understanding of this, and then time this portion, and then you may extend this into your knowledge. It's going to be D1, D2, and that is going to be this one. And K11, you don't need to make a copy of everything. If you like to, just put this one to be K11, and don't forget about the inverse. You must inverse it, and inside it, okay, you have what? You have minus 41 and plus 26.5. You got to show how you understand it, okay? And then the portion of this is going to be what? Is going to be, let me show you. This one, okay, time this one. The author will time 0, okay? That is going to be what? 45,000 times 0.01 is going to be 450, okay? You just put this one plus this one times this one plus 450, and then the next one you just time this one by this one again, and the author you just time 0. It doesn't require much energy to do so, but the first one negative times negative times negative, you get positive, but this one positive times negative, you get this one for negative 1,350, okay? And then after you put it properly into your calculator, it's not that hard. This portion just change to a number, and this portion just change a number and put it together. You get this one for be minus 4.366 to 10 minus 3, and then this is going to be in radian, okay? And then the other one going to be plus 3.22767 10 minus 3 and radian. When you have this, you may come to this one, okay, and you may see the number 1 here. We have the negative, so the rotation that occur here is going to be in the reverse direction of this, and you said this is going to be 4.3662 and 10 minus 3 radian. You're going to draw the elastic curve here again, and this one over here, the rotation gonna be in the positive, so it's gonna be something like this, and it's going to be in the same direction, both on the left and on the right. This is going to be 3.2767 10 minus 3 and then radian. Okay, and you can see the draft that I did is pretty good, but not correct yet until we get the moment diagram. Okay, that is going to be what we have. Now we're going to go further to determine the Q. Let me move it a little bit to this portion. Q3 minus 40. We have, let me put it, Q3 minus 40, Q4 minus 41, Q5 minus 9, Q6 plus 4.5, and this one will equal to this portion. You must copy this one, but you don't need to put everything. Just say this is going to be k sub to 1. Okay, this k sub to 1 will time this. So make a copy of the d that we have and time it with this one. Okay, this is going to be minus 4.3662 10 minus 3 plus 3.2767 10 minus 3, and then you get this. And this portion just plus this, just plus. But this way is up to you. You may do the computation again. Based upon this, I should tell you the first number that we can compute it easily by hand is going to be this one times this one. It's going to be 1350, and it's going to be negative because it's positive, minus 1350. And then you may time this one by this one again. It's going to be just 150, and negative you get plus 150. Okay, and then if you go, this is going to be minus and minus, that is going to be positive 1200, and the last one time this one is going to be negative 1800. Okay, and then you must understand that the Q3 based upon what we have here, this is going to be kilonewton, Q4 kilonewton, Q5 kilonewton, and this one kilonewton meter. So you will see what you are looking for. Now you take the computation of this. Can you do it by hand? It's up to you, because it's going to require this one time, this one plus this one time, this one. You got to do it very carefully. It's up to you. So the last one that you get is going to be the Q, in which is going to involve Q3, Q4, Q5, and Q6. Don't forget to move everything to interact with this. Okay, and then let me conclude. What did you get? After some computation, you will get this one for minus 671.16 kilonewton, and this one plus 141.97 kilonewton, and you get plus 619.19 kilonewton following this, and the last one supposed to be kilonewton meter. Just put the last one over here, and that is going to be your result. I get 1,200 minus 14.69, and you got to check for the equilibrium of this one 3 and 1.5. Okay, this one 3 and 1.5 cut over here, and this one and this one under application of this 6 kilonewton meter, and this one for 12 kilonewton meter, and also the moment over here for 20 kilonewton meter. What you get from this one, you know, the Q3. If we put this one back again, and based upon this, Q3 is here, and then it's going to be downward. Okay, and then this is going to be this way, 671.16 kilonewton. Q4 is over here, positive. This one 141.97 kilonewton, and then this one 619.19 kilonewton, and this one is going to be in the reverse. Okay, so this one going to be in this way, 1,214.69 kilonewton meter, and I should say you got to summation of f sub y and positive upward. Okay, that is 141.97, and then this one plus 619.19 and minus 671.16, and then you have this one to be 12 kilonewton per meter times 6 meter. So this one is downward, minus, right? Minus 12 times 6, and also you have this one minus 6 times 3. If you do so, you will get this one for 0.99 kilonewton. Is going may have some error. This some error due to the significant figure that we use in the computation. Okay, but not enough. You're going to check another one. Okay, summation of the moment. You may take the moment over node number 3, and then you may have this one the rotation in this way, 141.976 and 3. That is going to be 9 meter, and rotate this way is positive. This guy plus 12 1,214.69. Okay, and then you may minus is this one 671.16 times over here is 3, and then you also have this one minus 12 times 6 and 3 plus 3 times 6, and then minus this one 6 times 3 times 1.5 Okay, 1, 2, 3, 4, 5 member, 1, 2, 3, 4, 5 is supposed to be close to 0. If you check it and you get the result like that, that is going to be very good result. Okay, and that is going to be very, very correct. And then we come to determine the capital K. Okay, I took a lot of time on this. If you guys have something, you can go further. You can leave the lecture. But I like to finish everything. Okay, so please let me do that to show you guys this. Let's go a little bit further to the matrix Q. And you understand that the matrix Q can be defined from K prime, time transformation matrix, and capital B matrix by setting this local coordinate system when lambda sub x equal to 1, lambda sub y equal to 0. This guy going to be the identity matrix. So we will use K. That's we have the K from the previous one that we have here, K1, K2, times the capital D. Okay, so let's work on the first one. The first one, again, we have 4, 1, and 3, and 2. You just make a copy of this. It's going to be Q. This is in this direction. This is X prime. This is Y prime. Q, Q4, Q1, Q3, and Q2. Okay, and this is going to be the internal force, internal moment. Not yet until we combine with fixed and shift moment, but by definition of it. But by doing this, it's going to time. You don't need to copy everything. You said this one going to be K1. Just plug this K1 into your calculator, and it's going to be 4132. So this one will time the capital D matrix with D4, D1, D3, and D2. And you can see the D4 is 0. D4 is here. D1 have the number, D2 has the number, D1 have the number, D3 is the settlement, D3 is going to be minus 0.010 meter. D1 just take what we has previously from our calculation on the top of this. It's going to be minus 4.3662 10 minus 3 radian, and D2 is positive 3.2767 10 minus 3 radian. Just put them all together in the calculator. You will get the result, and then what you have for the result is going to be plus 100 plus 97 kilonewton minus 41.0 kilonewton meter minus the same thing. The same thing at top is always the same number. If you didn't get, you get a wrong answer. This is going to be 646.85 positive kilonewton meter. This is going to be the first one. Okay, and then for the second one, you use this one again, and then let me put it over here, and this one gonna be 3, 2. This is 3, this is 2, this is gonna be 5, and then 6 is gonna be Q3, Q2, and Q5 and Q6. Okay, and just plug it in like this, and it's going to be equal to this. You put this one for the K1. For this one, you copy this K2, okay, into this one, and then what you got to put is going to be the capital. This matrix is going to be D3, D2, D5. D5 is 0, D6 is 0, D3 is minus 0.010 meter, D2 is here plus 3.276710 minus 3 and radian. And then you do the calculator computation, you will get the answer like this: minus 610.19 kilonewton. This is going to be positive 610.19 kilonewton minus 220.39 kilonewton meter, and this one 1210.19 kilonewton meter. This is not the internal force and moment yet. Okay, you got to put the fixed end moment, fixed end shear into it. And let me put everything over here to make it a more complete in order us to do the shear diagram and moment diagram. First of all, you guys must understand the fixed end shear, fixed end moment that we have over here. Just copy this one. You must copy this one into this. Let me do it over here first. 3 and 2.5. Just move it a little bit, okay? And then we have that, and then we have the area to work on it. This one 3 meter. This one 1.5 meter. This one subjected to uniformly distributed load 12 kilonewton per meter. This is 6 kilonewton per meter, and then you also have the moment 20 kilonewton meter, and copy everything. Okay, that's you has this. This one 41 kilonewton, this one 31 kilonewton, and 41 kilonewton meter. This one in combination 31 kilonewton meter, 31 kilonewton meter, and then 4.5. Put this one into 4.5 kilonewton meter, and then you have this one for 9 kilonewton, and this one also for 9 kilonewton. And don't forget about this 4.5 again. This is going to be 4.5 kilonewton meter. You got to combine this one with the result that you get over here. So move this one out and take this result into the position, and then do the same thing. You put this one as the member number 1, and this one is the member number 2. You got to take everything. What is going to be 100.97 is upward. So 100.97 is upward. This is going to be 100.97 kilonewton. This is downward. Okay, this is going to be 100. Oh, sorry, 100. Actually, I should move this one a little bit. 100.97 kilonewton. How about this one? This one 41. This one gonna be this negative. Okay, positive gonna be this way. Okay, they're like this one this way. This is gonna be negative. So 41 kilonewton meter. There is no load here. And then 646. This is going to be very large one. 646.85. Let me put this one. 646.85. 6.85 kilonewton meter. Okay, and then we come to this one negative. So this one taking a downward and this one taking a upward. 610.19 kilonewton. 610.19 kilonewton. And then negative 620. Negative is negative. When it's negative, it's in the opposite direction to this. So what you get is going to have the 620, and then you will get this one. It's the reverse, the direction of this. That is going to be 620.39 kilonewton meter, and the last one is going to be the negative. Okay, opposite to this is going to be 1,210.19 kilonewton meter. And then you got to combine it, and let me put this member onto this one in order me to draw it a little bit easier. And when you combine it, don't forget to bring the load over here, 6 kilonewton per meter, and this one is going to be 12 kilonewton, 12 kilonewton per meter. Just move to the right, okay, and then per meter, and 20 kilonewton meter is here. And by combining, you can see this one and this one, they delete each other, and then it's going to be 0. That's going to close to this one because it is lower here. Okay, for this one, 141.97 kilonewton and upward. That is going to be what we have. And then next, this 31 is upward, this one is downward, so this one will be downward. Take this one minus 31, you will get this one to be 69.97 kilonewton. Now this one and this one go together. You combine this one by hey, is that correct? No. Let me check. 6, 4. And that's correct. No, this is 6. 646.8. This is wrong. This is positive. This is supposed to be in this direction. Okay, this is wrong. This is going to be in this direction. Is positive. See, it's positive, right? It's positive. It's going to be Q. This Q, and then sorry, this is correct. Okay, make it correct, and then this is correct, and then this one is upward. This one is counterclockwise. This is clockwise. So let's delete it, and then we get this moment to be 615.85. 615.85 kilonewton meter, and then we move it to the second one. This is 9. This is 600 something. That is going to reduce it. Reduce by 9. 601.19. So this one is 601.19 kilonewton. And this is 610 plus 9. This is going to plus. This one is going to be 619.19 kilonewton. And the moment, this one 4.5, this one minus this one by 4.5, you go to 615.89, and the direction gonna be in this way, 615.89 kilonewton meter. Oh, this is not the same, but is close enough. Okay, this is the balance of the moment of choice of node number 2. This is important to check. Okay, and the last one, this one 4.5, 1214.69. Now, okay, this one 1214.69 kilonewton meter. Now you are ready to draw the shear diagram. Okay, if you prefer to draw it, just make it to be. I put everything like this, so don't worry. This is going to be x meter 0, 3, 6, 9, and then put this one into V kilonewton. And let's to draw the shear diagram. First, we move from the left to the right again, and then we have this one for 141.97. Let me put scale of 200 kilonewton per 10 millimeter. So I will get this one about 7 millimeter. Okay, and then I can use this one 141. Okay, I can write again 97 kilonewton, and then that is going to be 7 millimeter, right? It's going to be here, and then we have the dV by dx equal to minus W. So dV by dx going to be minus 12, and then to be over here, if you are good at drawing this is going to take the downward, and then you will know that this one will require the downward of 69.97. Okay, that is going to be about 3 millimeter, and then your slope will be like this. And if you prefer to make it very correctly, you just put this one together, and then by making this one as the half, just plus this one by this one divided by 2, you will get this one to be 105.97. Okay, and then come to the second one. This one going to take you 601.19. By scaling this, you will take it for 30 millimeter minus 601.19 kilonewton, and then you have the dV by dx equal to minus 6. This one gonna get downward, and see you can get 6 larger than this, minus 619.19. By doing this, it's going to be like that, and then the slope is going to be something like this, minus. Why I know this? Because it's going to take this one upward for 619.9. This is going to be minus 619.19 kilonewton, and take this one up to close it, and this is going to be the slope, and that is going to be the shear diagram. And for the moment diagram, you may take this as the m kilonewton meter, and this has no moment. It's going to be 0 moment, and then by setting x meter, you may have the moment diagram like this. And by doing this, this is going to be the shear. dm by dx equal to plus 141.97. This one gonna upward, okay, and then it's going to come in this way. The moment here minus 0 is going to be the area here, 1/2 of 141.97 plus 105.97, and this is going to be 3 meters. The moment is going to be sum this and times 1.5. I get it for 371.91. 371.91 kilonewton meter. Now you got to use your scaling again. Use the scale 200 kilonewton meter per 20 millimeter, because over here is very large. If I use 10, I'm going to have, wow, that is going to be 12 centimeter. That is too much, okay? And following this one is mean 100 per 10. That is still large. It's still large. Let me put it in like 400 per 10 millimeter. Okay, that is about 9 point something millimeter, and this is going to be the value of the moment here, and then the slope over here will follow the shear over here. So the dm by dx is going to be 105.97, and the curve will follow this one as we know. And now this is counterclockwise. When it's counterclockwise, what happened is the value of this gonna be decreased by 20. This is going to be 351.97, okay, to be exact. And then this is 105, and then it's positive. So the slope over here will follow this value. Put it clearly where it is. And the moment here, don't worry, the moment here and moment here in the head and head is positive 615.85. Okay, that is about 1.5 centimeter about this, and just put this one 615 point. If you like to clear it, it's maybe 0.87 kilonewton meter, and the slope over here will follow the shear over here. The shear over here is 69.9. dm by dx is going to be positive 69.97, and then your curve going to be something like this, okay, and make it as a curve. And then coming to this, your shear chain is going to be downward, very big downward over here. This the shear dm by dx going to be minus 601.19, and then due to this one, the m and here for is going to be negative, so it's negative for 3 centimeters something, okay, it's going to be negative over here, minus 1214.69, and then you have what? You have this one for 619.19. So the slope here is very high. And then you said dm by dx. dm by dx. How come it's one focus? Very strong. Okay, let me put this one. It's maybe focus a little bit better. dm by dx is going to be minus 619.19, and then your curve is going to be something like this, and then you will see this is going to be the point of zero moment. Okay, and following what we have of this, you may project this and mark this point as your inflection point to make it to be the inflection point. Okay, that is all we have for this one. When you mark the inflection point at this point, your elastic curve will be correct because it has what? It has the rotation here, the rotation here, the inflection point here, and this is zero. And that's all for today.